So today we'll be finishing the discussion of combinatorics and also going over conditional probability. So the previous discussion of combinatorics, we were mainly considering mostly considering various forms of what are known as permutations. Today we're going to consider the combinations which generally implies that the sample you're selecting is unordered. The general question we want to answer, as it says here, is say you're selecting R objects from a population of N objects and order does not matter, and we'll suppose for the time being that the N items are distinct. So let's say that we have 4 objects. Then, as you'll recall from the previous discussion, or from Tuesday's discussion, that there are a total of 12 possible ordered samples, each of which are listed here. But if we assume the order does not matter, then we note that AB is the same as BA, AC is the same as CA, so on down the list. So even though there's 12 ordered samples, then there's only 6 ways, or only 6 unordered samples, because half of them are redundant. And thank you, UNC, for letting me know that it's protected in the middle of my lecture. So in general, the formula here is that given if there's 12 possible ways of choosing ordered pairs, and for each of these ordered pairs, there's 2 factorial possible orderings, or just 2 in this case, that we don't care about. So the number of unordered pairs is just going to be 12 divided by 2, which of course is equal to 6. And so this formula in general, if you've had a probabilistic or combinatorics class in the past, you've probably seen this before. But in general, the number of ordered samples is going to be equal to the number of combinations times the number of ways of permuting each ordered sample. Oh, in other words, based on the Tuesday's formula, n factorial over n minus r factorial will be equal to the number of combinations times the number of ways of ordering each ordered sample, which of course is just r factorial. It's the number of ways that you can permute r things. So the total number of combinations is going to turn out to be n factorial over n minus r factorial times r factorial, which can be denoted as, in this little parentheses, n over r. The way you say it is n choose r, and that's obviously equal to n choose n minus r as well. And you can show mathematically that if you have a population of n elements, then there's n choose r different combinations or different subpopulations of size r, where r is less than or equal to n. Or you can say n choose r represents the number of possible combinations of n objects taken r at a time. And just to make the math work for some of the theorems we're going to discuss later, by convention you say you define that 0 factorial is equal to 1, and hence anytime n choose 0 is, and hence n choose e 0 or n choose n is also equal to 1. And if you try to choose n choose r when r is greater than n or less than 0, then you define that to be 0. Oh, a couple simple examples of this. Say you have a group of 5 women and 7 men. You need to form committees consisting of 2 women and 3 men. Hopefully this is straightforward enough, and I won't ask you to answer these. It's just going to be 5 choose 2, which is the number of possible committees of women, and 7 choose 3 possible committees of men. And since And since these two committees are formed independently of one another, the total number of committees, you can just multiply the two together. Turns out to be 350, assuming I didn't make more math mistakes when I'm computing combinations late at night. And if we do some poker examples here, I'm just assuming that you get 5 cards, no redealing or anything like that. You just, what's the probability of getting a certain hand in these 5 cards that were dealt? First of all, we need to compute how many different poker hands are possible. That's, of course, going to be 52 choose 5. There's 52 cards in a deck. We're choosing 5 of them. The order of the cards does not matter, so use the combination formula. There's approximately 2.6 million different possible poker hands. So let's say you want to compute the probability of getting 4 aces in your poker hand. Well, the way that you would go about doing this is you count the number of different hands where you get 4 aces divided by the total number of possible hands. So what's the probability of getting 4 aces? Well, you have 4 of the cards, you already know what they are. You have to have the ace of diamonds, the ace of clubs, the ace of hearts, and the ace of spades in your hand in order to have the 4 aces. And the 5th card can be anything that you want. There are 48 remaining cards. So there are 48 possible ways you can get a hand containing 4 aces. So you divide that by the total number of possible poker hands, and the probability turns out to be 1.8 times 10 to the minus 5. Make sense so far? Any questions? So let's make this a little bit trickier. Let's say rather than the probability of getting 4 aces, let's say what's the probability of getting 4 of a kind? Well, in this case, it's going to be 48 times 13 possible ways that you can get 4 of a kind, because once again, 4 of the cards have to be the same, but they can be any card between aces to tens or jacks, queens, or kings. There's 13 possible things that your 4 of the kind could be, and then the 5th card can be anything. So 13 times 48 possible ways you can get 4 of a kind, once again divided by 52 choose 5 to get a probability of 0.00024 of getting 4 of a kind. Now let's say we want to compute the probability of getting 3 of a kind. That's even a bit more complicated. First of all, we need to compute the number of different ways that you can get 3 of a kind. So there are, once again, the 3 of a kind, there's 13 possible cards, so your 3 of a kinds can be in aces, 2s, 3s, up to 10s, up to kings. There are 13 possible numbers for your 3 of a kind, but this time, with 4 of a kind, in order to get 4 of a kind, you had to have clubs, diamonds, hearts, and spades, all 4. With 3 of a kind, you're only going to have 3 of the 4 suites. So, given the 4 possible suites, we're choosing 3 of them. So that's going to be equal to 4 choose 3, which of course is equal to 4. Another way you could think of it is just in your 3 of a kind, 1 suit is going to be missing. There are 4 possible suits that could be missing. The total different number of ways that you can get 3 of a kind is therefore 13 times 4. So getting 3 of a kind for 3 of your cards. And then you need to multiply that by the number of ways of getting 2 more cards, which are not pairs and not the 4th one. And the simplest way to think of this is one of the 2 cards can be can be anything that is not whatever your 3 of the kind is in. If you have 3 2s, it can be anything that's not a 2. So there's 48 possibilities for the 4th card. For the 5th card, it gets even a bit more complicated because, once again, it cannot be, we'll say that you have 2 2s and a 3. You cannot have another 2, or you would have 4 of the kind. And likewise, you cannot have another 3, because then it would be a full house. You just want 3 of a kind. So it has to be, if you have 2 2s and a 3, the 4th card has to be something that's not a 2 and not a 3. So there's a total of 44 possibilities. And then we divide that by 2 because the order in which you draw these final 2 cards doesn't matter, so we have to divide it by 2. So the total number of different ways that you can get 3 of a kind is going to be 13 times 4 choose 3 times 48 times 44 divided by 2, which turns out to be 54,912. And to get the probability of 3 of a kind, you divide that by 52, choose 5, and get about 0.021. Makes sense thus far? Nobody's completely lost and will be traumatized like they were last week? Okay. And a famous theorem in mathematics generally, not just combinatorics, is what's known as the binomial theorem. If you've had analysis or even advanced algebra, there's a good probability that you've seen this before. But the binomial theorem says if n's a positive integer, then you can show that a plus b to the nth power is just going to be the sum from 0 to n of n choose r times a to the r times b to the n minus r. The proof is a homework problem. You can do it by induction or by Google. Whoops, did I say that out loud? But yeah, it's just a really famous theorem that's probably proved in about 500 different places, but it's a good exercise to understand proof by induction, regardless of whether or not you do it yourself. And a couple important special cases of this is if a plus b equals 1, then that gives you that the sum from 0 to n of n choose r times a to the r times 1 minus a to the n minus r will sum to 1. The reason we care about that is because if you've ever heard of the binomial distribution before, which is a very common standard distribution that you use in statistics, that expression right there is the density function for the binomial distribution. Density functions have to sum to 1. The binomial theorem tells us that it does indeed sum to 1. More on this in a week or two. And also, if we let both a and b equal to 1, then you get the sum from r to n of n choose r is equal to 2 to the n, which implies that the total number of possible subsets of x1 to xn is equal to 2 to the n, because it would be the sum of the number of subsets of size 0 plus the number of subsets of size 1 plus the number of subsets size 2 and so on. So hence the famous result that the number of possible subsets of a set of size n is 2 to the n. And I probably should have switched the order of these next two slides. The Pascal's triangle that I'm going to show you in the next slide is an illustration of this result. You can show n plus 1 choose r is equal to n choose r minus 1 plus n choose r. Again, it's a good induction proof that will be in the next homework assignment. And this becomes, the reason this theorem is kind of famous is because you can do this kind of cool triangle thing where you just write the various different combinations in the form of a triangle. Top of the triangle, 0, choose 0. The next row is 1, choose 0, 1, choose 1, 2, choose 0, 2, choose 1, 2, choose 2, and so on. Each row of the triangle, you increase the top of the combination by 1, and then you do the bottom part of the combination from left to right. What the theorem on the previous slide tells you is that if you create this triangle like this, then every single element in the triangle is just the sum of the sides of the triangle are all equal to 1. Anything that's not on the side of the triangle is equal to the sum of the two numbers above it. For example, 2 is equal to 1 plus 1, 3 is equal to 1 plus 2, 4 is equal to 1 plus 3, 6 is equal to 3 plus 3, etc., etc. So that's just kind of one of those fun math things if you're into geeky math stuff. If not, then you just grit your teeth and do the homework, I guess. And next, we'll consider partitions. As we touched on it briefly in the previous lecture, that say that you, rather than just finding a single subpopulation of size R in a larger population of size N, let's say we want to find a couple different subpopulations, that the total number of subpopulations sum to M, or sum to N, the size of the total population, and the first subpopulation contains R1 elements, the second subpopulation contains R2 elements, etc., etc. Then the total number of ways that you can partition it into these subpopulations is going to be n factorial over R1 factorial, R2 factorial, times up to RK factorial. I mean, I guess we kind of went over this on Tuesday, so I won't belabor the point, but so we all remember how to do this. If you have 10 children divided into Team A and Team B, and there's 5 kids on each team, the total number of possible divisions will be just 10 factorial over 5 factorial times 5 factorial, 252 possible divisions. Everybody with me so far? Okay, good. Mm-hmm.
So it says K 4 pairs.
Mm-hmm.
So we're back in permutations?
No. Just, there's no ordering within... There's no ordering within each subpopulation. It's just the subpopulations themselves have some sort of ordering in them. And now we get to the occupancy problem, which I will be honest on this one, just if for no other reason, so that if you have trouble with any of the material in this class, it doesn't mean that you're like dumb or that you don't belong in grad school or anything like that. To be honest, maybe I had seen this problem somewhere time before I was preparing this lecture last night, but if I did, I don't remember it. And like when I first stared at this, I'm like, where did that formula come from? This makes no sense. And I don't know if I should confess to how long I stared at this before I managed to wrap my brain around it, but it was like an hour or two. Now, some of that may be due to sleep deprivation, so I will try to explain it such that you have an easier time grappling with this than I did, but just thought I would give fair warning and don't feel bad if this is not immediately intuitive, because it sure as heck wasn't for me. So, the occupancy problem in the classical statement of the problem is, say you have indistinguishable balls we want to place into our distinguishable urns, so how many different outcomes are possible? That, and mathematically you can think of this as, say you have a vector x1 up to xr, and each xj is the number of balls that you put into the jth urn, and we have to put every single ball into an urn, so the total number of balls in the urns has to sum up to n, and we're looking for the number of different ways that you can put n balls into R urns. So, how can you compute that using the formulas that we've considered thus far? Well, the way I finally managed to wrap my brain around this, I may have to draw some pictures on the blackboard here to try to help illustrate this. Those of you watching this on YouTube, I apologize. But you can think of it this way. I mean, the way we put it in the lecture slides is there's n minus 1, say, a piece of chalk here, okay, I guess inside here there is. Let's just say let's just list all the balls manually. We have ball 1, ball 2, ball 3, up to ball n. And to count the number of different ways they can be divided into urns, we'll think of it as, we'll just put dividers along here somewhere. We'll just say, here's a divider, say here's another divider, etc., etc. And anything to the left of this divider goes into the first urn, anything between these two dividers goes into the next urn, and so on. In fact, maybe I'll just try to make this even more concrete. Let's say that we have 7 balls. I'll just list every single one of them. Everybody see this in the back? Maybe I should have written bigger. Let's say we're putting them into 3 urns. So you can just say, let's say we put a partition there and there, for instance. Then B1, B2, B3 go into the first urn, B4, B5, B6 go into the next urn, B7 goes into the final urn. So you can think of this as, since for the time being we are assuming that these urns are not empty, that each divider is going to be associated, is going to be to the right of one possible ball. So in this case, B3 and B6, but it can only be to the right of the first 6 balls because we're assuming they're non-empty. If it were to the right of B7, then that would imply an empty urn, which we're trying not to have here. So essentially what it boils down to is a combination problem where there's 6 possible objects and we're choosing a set of 2 of them. So 6 possible spaces between the objects, we're choosing 2 of them to generate the partitions. So the total number of possible partitions of balls into urns would just be n-1, choose r-1 in general. That makes sense, sort of, kind of, almost. I mean, like I said, I stared at this for like forever before I wrapped my brain around it, so don't feel bad if you're not digesting this immediately, and I hope I'm not having just scared everyone into not understanding it by saying it, but I just figured if I had to stare at this for an hour, that I probably wouldn't be the only one. I can't tell if people understand or everybody's just afraid to admit that they don't understand, but any specific questions, or should I just go on with the understanding that you may need to stare at this more later? Okay. Now, the even hairier case where some of the urns are allowed to be empty, in this case, the way I visualized it is same sort of scenario, but in this case, we can't assume that each partition between urns is going to be attached to one of the balls, because we could have like 2 partitions right next to one another with no balls in them, because In this case, we're allowing for the possibility of empty urns. So in this case, you would write it down as, you could say something like ball 1, ball 2, partition 1, ball 3, ball 4, ball 5, ball 6, partition 7, ball 7. So basically we're looking at total number of possible orderings of these n plus r minus 1 objects. In this case, there's a total of 9 objects because we have 7 balls and 2 partitions. So the number of different ways you can order this sequence is obviously just going to be n plus r minus 1 factorial. But given a particular ordering, the ordering of the balls is redundant. We don't care about the ordering of the balls. So that means that we're overcounting by a factor of n factorial, because there's n factorial different ways that the balls can be ordered. And similarly, we don't care about the ordering of the partitions. I'm coming to think that this should be P2, not P7. Sorry about that. In this case, there's only 2 possible orderings. It's either P1, P2, or P2, P1. But in general, given r minus 1 partitions, there's r minus 1 factorial different ways that the partitions can be ordered. So the total number of ways that these balls can be partitioned into urns where there's possibilities of empty urns is going to be n plus r minus 1 factorial for n factorial times r minus 1 factorial, which of course is just equal to n plus r minus 1. Choose r minus 1, the formula that's in the book and the notes and so forth. Makes sense, sort of?
So in the first one, we're thinking of r is greater than or equal to
Less than or equal to n. We're assuming less urns than balls. And does it even make a difference? I haven't really thought through that scenario. I designed this example under the assumption there's less balls than urns, although as I think about it, I think the same logic would work. Well, would it? Yeah, for the first scenario, I think you do have to assume r is less than n. The second scenario, I think, may still work because you're allowing for the possibility of empty ones.
It's practically, the second problem is equivalent to choosing the possible ways of picking. Like you are just picking r minus 1 dividers out of a total of n plus r minus 1 items, and it's as if you are picking like some unordered dividers out of the total number of objects. So it's just n plus r minus 1 truth numbers.
Yeah, precisely. So, like I said, it took me quite a while to wrap my brain around this, so don't feel bad if you don't get it immediately. Hopefully this is not as traumatizing as non-measurable sets, but if anybody has questions, I'm happy to go over this in more detail. If you just need to stare at it, fine. If it makes no sense whatsoever and you just need to memorize the formula to regurgitate it on the exam, I guess that works too. Any questions about this before I move on? So again, you can show mathematically using essentially the logic that I outlined here is that if you want to find the number of positive integers x1 to xr such that x1 the sum of x1 to xr equals some positive integer n, where all the xj's are greater than 0. Then there's n minus 1 choose r minus 1 distinct ways that you can do that. And if you allow the possibility that some of the x's are equal to 0, then there's a total of n plus r minus 1 choose r minus 1 non-negative integers such that their sum is equal to n. So, even if you don't entirely understand where the formula came from, how many distinct non-negative integer values of x1 plus x2 equals 3 are there? Wow, no one. Okay, nice to know that I'm not the only one who struggled with this. Any courageous soul before I just revealed the answer? Yeah, exactly. It's going to be 3 plus 2 minus 1, or 4 choose 2 minus 1, which is equal to 4. And now a slightly more complicated example. Let's say that you have 20 cases of flu vaccine to distribute to 4 hospitals. So the first scenario, we're assuming that all of the vaccine must be distributed to these 4 hospitals. How many different ways can it be distributed?
If you want non-negative,
Yeah, so we're using the non-negative formula here, and in this case, or actually, no, we are not using the non-negative formula here, sorry. The idea was, in the first case, we're assuming that at least some is distributed to all 4 hospitals. There would be 23 choose 3 possible ways to do that. And if some of it's held in reserve, then that's basically equivalent to a fifth urn, the part that's held in reserve plus the part that's distributed to the various hospitals. And there would be 24 choose 4 possible ways to do that. And as I think about that, maybe that should have been modified, because if we're assuming that some of it's held in reserve, then we wouldn't be interested in the case when 0 is in the reserve group, but, you know, whatever. Make at least some sense.
So for the first case, you're saying that it's possible for one hospital to not get any vaccine?
No. No, that's correct, sorry. Yeah, like you said, I was confused by this stuff too. The idea is that the health department keeps some of the vaccine themselves rather than distributing it to the hospitals. So that's effectively a fifth urn in this case, that there's the held back urn plus the 4 hospitals urns. So R becomes 5 instead of 4. And this is Stirling's formula, which I guess you sometimes use for proving certain things, and you sometimes use for computing factorials in computers, at least I think. Quite honestly, I'm not really sure what you use this for or why we care about, but people who prepared these slides previously thought this was important enough to put on a slide, so I put it on a slide, and unless it shows up on the homework, you can probably forget about it. Alright, now we will switch gears to conditional probability and independence. This is, I think, chapter 1.3 in Cassell and Berger for anyone who's following along there. Again, if you've had a probability class, you're probably familiar with the basic idea behind this. But if not, then I'll explain the basics. That if we assume that an event B has non-zero probability, then we can say the conditional probability of the event A given B is the probability of A and B divided by the probability of B. That this formula may be easier to see intuitively with a Venn diagram. Say the big box is our larger omega, and say this circle here is B, and then say there's this smaller event A within B. It doesn't necessarily have to be within B, but just for the sake of illustration, normally to find the probability of A, you would take the area of A divided by the area of your entire sample space. Conditional probability means that you're given that event B has already happened, so you know that your particular outcome is not outside of B. So the conditional probability, rather than dividing by the area of the whole sample space, you would only divide by the area. You would take the probability of A and B, the intersection of the two areas divided by the probability of B. That if A went out there outside of B, you would only consider the part in both A and B, because you know that B happened, so you know this area cannot happen because it's outside of B.
So if we see like probability of B, that's just understood that it's like probability of B given.
Yeah. In fact, that's basically the next equation on the slide, that in general, probability of A given omega is always going to be equal to probability of A. And as we've discussed before, disjoint events are events that cannot happen simultaneously. If you draw one card from a deck of cards, you cannot simultaneously draw the 2 of clubs and 3 of diamonds. And if 2 events are just disjoint, that is, if their intersection is empty, then the probability of A given B is 0, and the probability of B given A is 0. If you know that you've drawn the 3 of diamonds, then the probability that you drew the 2 of clubs is equal to 0. And conditional probability satisfies all the probability axioms just like regular probability does, that the probability of, it's easy to show the probability of the sample space given that B is just equal to B. Likewise, conditional probabilities are positive, and given a series of disjoint events, the probability of their union is just the sum of the individual sum of the individual probabilities. Similarly, the probability of the empty set is 0, the probabilities for less than or equal to 1, and the probability of the complement of an event is just 1 minus the probability of the original event conditioned on B. And 2 events A and B are said to be independent if the probability of A intersect B is equal to the probability of A times the probability of B. And if you go through the formula for conditional probability that I just outlined, that the probability of A given B is going to be equal to the probability of A and B times the probability of B. Well, by the definition of independence, probability of A and B is equal to probability of A times the probability of B. Probability of B's cancel, you get the probability of A. Similarly, the probability of B given that A equals the probability of B. And this probably agrees with our intuition of what an independent event means. That means that given that you know that a certain event happened, given that you know that a certain event happened, it doesn't give you any information at all about the following event. If I flip a coin 2 times and the first one lands heads, the probability the second one lands heads is still 50%. The fact the first one lands heads, assuming the coin is unweighted, doesn't give me any information about the second event. And you can show that if A and B are independent, so is A complement and B, A and B complement, and A complement and B complement, and also raising the homework question of is it possible for 2 disjoint events to be independent, and is it possible for 2 independent events to be disjoint? And you can also talk about the independence of multiple events, that events A1 to AN are said to be mutually independent if every single possible subcollection of the events is independent, that you take any pair of 2 events and they're independent, you take any set of 3 events or a set of 4 events or whatever, they're all independent. And note that this has to be true for every possible subcollection. Just because every possible pair of events is independent, that does not imply that the events are mutually independent. And only if this condition is satisfied can you get the probability of AJ for arbitrary J given all of the other events is just equal to the probability of AJ. That, for example, if you toss a coin 3 times and say like H1 is the first one is ahead, H2 is the second one's ahead, H3 is the third one is ahead, then again assuming the coin is fair, then these events are independent and mutually independent as well. But if you do a slightly more complicated definition where you say like A1, 2 is the first 2 tosses are the same, A1, 3 is the first and third tosses are the same, and A2, 3 is the second and third tosses are the same, then A1, 2 and A1, 3 would be independent of one another. For example, if the first toss is equal to the second toss, that doesn't tell you anything about whether or not the first toss is equal to the third toss, but the 3 events together are not independent. That if you're given that the first toss equals the third and that the second toss equals the third, then you know that A1, 2 also has to be a true statement, because if the first and third and the second and third are all equal, that implies the first and second are also equal. So this is an example of 3 events that are independent pairwise, but they're not mutually independent, all 3 taken together. And it's also, and this idea of conditional probability is useful for computing probabilities of sequential events that say you want to know the probability of getting 2 aces in a row. Well, you could do something like find the probability that the first one is an ace, which is going to be just 1 out of 13. Then the probability that the second one is an ace, given that the first one is an ace, which is not going to be quite 1 out of 13, because for starters, there's only 51 cards remaining in the deck, and only 3 of them are aces now. So rather than being,
It's long, 17.
what did, oh, You're faster at doing math in your head than I am. Yeah, you're right. I was just going to say 3 out of 51 because there's 3 aces remaining in the deck and 51 total cards remaining in the deck, so 3 out of 51, which is in fact 1 out of 17. Similarly, the probability the third one is an ace, I believe, would be 1 out of 25, 2 out of 50, and so on. And an example of this, if you wanted to compute the exact probability for the birthday problem, that say you have n students in your class, the probability that at least 2 of them have the same birthday, then say we just have some arbitrary order of the students. We want to be the DJ event that the first J have different birthdays. Well, I thought I had written the formula on here. Apparently I didn't. Sorry about that. But it would be, so the probability that the first 2 have different birthdays, that's essentially the probability the second student has a different birthday than the first student, which is going to be 364 out of 365. Now, the probability that the third student doesn't have the same birthday as either of the other 2. Can have any of, still all 365 birthdays are possible, but at this point 2 of them are taken, so it becomes 363 out of 365. And likewise, get the probability that they all have different birthdays, you can just keep doing that multiplication. Oh, if you do that, you can draw the graph of the probabilities, and at first, the probability of having multiple birthdays is fairly low, but as you can see, the probability gets to be around 50% with about 25, 26 students in the class. Once you get to about 40 students in the class, there's almost a 90% probability, I'm sure, if we went around the room. And here, the probability there's at least one birthday repeated would be quite high. And these conditional probability rules are sometimes useful for the way this slide describes is turning around probabilities, that it may be that the probability of A given B is hard to compute, but the probability of B given A is easy to compute or easier to compute or something like that. The example on this slide is that I guess the idea is that it may be hard to compute the probability of thunder given that it's raining, but you know that given that there's thunder, there's almost certainly rain, so you could compute the other way around like that. It's kind of a strange example. Maybe I should have put in a different one, but this is an example of what's known as Bayes' rule. That question? Oh, you're just stretching. Okay. This is an example of what's known as Bayes' rule, that you would, like it says, it's often used in the context where we want to know the probability that a certain hypothesis is true. Then you update this a priori belief after you've seen some data, that you assume that baby boys are just as likely to be born as girls, and you also know that 90% of baby boys plays with trucks, and that baby X plays with trucks, then what's the probability that baby X is a boy? And so I think about, did I forget to work that out? Yeah, I forgot to work that out. Oh, wow. It's a fairly simple exercise to do at home if you want to plug in the formulas. So, to formally prove Bayes' rule, the first thing we need to prove is this decomposition form for total probability, that we say, let A1, A2, up to AN be a partition of the sample space. Doesn't necessarily even have to be finitely many, although in most cases that we care about there will be. then you can show that the probability of any given event B is going to be the probability of the sum of the probability of B given that AI times the probability of AI summed over all the possible AIs, which kind of makes intuitive sense. Since the A1s form a partition of the sample space, that means all possible events are contained in at least one of the A1s, so you can say the probability of an event B, the probability of B given the first event happened, the probability of B given the second event happened, and so on. So the formal proof looks like this, that if we let S be the union of all the AIs, then I guess, come to think of it, I think that's probably a typo. That should just be omega, not S. But B is going to be equal to B intersect omega, which of course is going to be B intersect the union of all the A's, because by definition, the A's are a partition of omega, so the union B omega, which, using, I think that's De Morgan's rule, that's going to be equal to union from 1 to n of AI intersect B. And then we just use the formula for conditional probabilities, that the probability of B is equal to the sum of probability of AI intersect B. Since the AIs are by definition disjoint, then then you can just sum the individual probabilities. The formula for conditional independence, that gives us the sum of the probability of AI times the probability of B given AI.
I have a question though on the previous slide.
Mm-hmm.
For your example, aren't you missing a piece of information that is the odds that a baby plays with ducks regardless of gender?
That's a good point. I think you're right. Yeah, well, this is the dangers of recycling lecture slides from earlier people and putting them together late at night. By the time I got to this point, I was just like, I figured out that whole occupancy problem thing. I'm just going to coast through the rest of this lecture.
So because you have probability of B given A and you probability A, and you don't have probability.
Yeah, I think you're right. Yeah. And so, given that partition rule, then we can prove what's known as Bayes' theorem, which says that given a partition of the sample space, that a probability of AJ given B is going to be equal to the probability of B given AJ times the probability of AJ, divided by the sum of the probability of B given AI times the probability of AI. In practice, probably 95% of the time, the partition will just be A and A complement, in which case the denominator this will just reduce to probability of B given A times the probability of A, and the denominator will just be probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. But if for some reason you wanted to do a more arbitrary partition with more than 2 elements rather than just A and A complement, you can using that formula.
So, sorry, just to make sure I'm understanding this correctly. So the denominator in that is all the possible ways you could get B in the set, in all the sets like A1.
Yeah.
Okay. Great.
And the proof for that is fairly straightforward given the formula on the previous slide, that probability of AJ given B using the formula for conditional probability is just going to be the probability of B intersect AJ divided by the probability of B. Then the numerator, of course, is just going to be probability of B given AJ times the probability of AJ divided by the probability of B and then the probability of B is equal to that expression based on the result from the previous slide. And I'll just note in passing that particularly if hypothetically you ever have to take a qualifying exam where you're not allowed to use notes or only a limited number of notes, it's worth understanding the arguments behind this proof, because I don't know about you, the first time I saw Bayes' rule, I'm like, oh my gosh, that is so convoluted, how am I ever going to remember this? Well, if you just remember the formulas for conditional probabilities, it's fairly easy to derive that, like I said, the vast majority of the time, this partition will just be A and A complement. So if you want to find the probability of A given B, then just go to that step using the rules for conditional probability, change that to probability B given A times the probability of A. Then the denominator you can calculate just by saying probability B given A times probability of A plus probability B given A complement times A complement. You can remember where the formula comes from. You don't have to try to pack the whole complicated formula into your brain in the event that it shows up on an exam someday. So, an example of Bayes' rule is, this is a paradoxical result that's a famous example in these types of statistics classes where you're doing some type of screening for a disease that say that there's a disease D, we'll just say D means you have the disease, D bar means you don't have the disease. Say you do some sort of diagnostic test to see if you actually have the disease. T plus means the test is positive. T minus means that it's a negative test. And this example here is based on some actual numbers on a diagnostic test for cervical cancer. And one of the things you want to know about these tests is the positive predictive value, which is given that you have the disease, what's the probability that your test is positive? Or I said that the other way around. Generally, you will know that, and let's say you have a positive test, what's the probability that you actually have the disease? So in this case, like a cervical cancer example, the probability of cervical cancer, we're going to say, is 1 in 21,000 to the best estimate of the annual incidence rate. So we say the probability of D to be about 0.0004. And the sensitivity of the test, which is the probability that you get a positive test given that you have cervical cancer, is going to be 0.71, and the specificity, which honestly 1 minus the specificity is usually more informative, which is the probability of getting a negative test given that you don't have the disease, is going to be 0.7. There might be. What do you think's wrong? So I will admit I did not go through this very carefully. I just kind of took...
No, there's not.
Okay. Well, it looks like there's a probability, or it looks like there's a typo, is dense a word? I've never heard of that before. I think that's supposed to be hence, but oh well. So, given these numbers, say we want to find what's the probability that you actually do have cervical cancer given you have a positive test. And it actually turns out to be quite low, on the order of 0.0001, like on the order of 1 in 1,000. So given 1 million positive results, only about 135 actually have cervical cancer. And this occurs as a result of the fact that it's just a rare thing that we're screening for in the first place. So even though if your test is positive, you're much more likely to have the disease than if the test is negative, the vast majority of tests are going to be false positives just because the overwhelming majority of the people who take the test don't have the disease, so the probability of a false positive among someone who doesn't have the disease is far greater than the probability of a true positive among someone who does, because the second group is tiny. And so, yeah, anyway, I guess that's the end of that example. The notes I had some additional examples that had to do with odds ratios and disease risk and stuff, but I thought that was kind of boring, so I put in another example that I think is much more interesting, just because, like, I've discussed this example with even smart math people who should understand probability, and they were just like, what the heck? You're smoking crack, Eric. There's no way that you're right. But I'm right. I'll show you here in a minute, and hopefully I will convince you that I'm right. I don't know if you've ever seen this problem before. If you haven't, it's a cool thing to bring up at parties because it's highly counterintuitive. But the Monty Hall problem comes from this old television game show called Let's Make a Deal. The host was named Monty Hall. The premise of this show is, I guess, the bonus round at the end. The contestant has to pick one of three doors. They know that, like, behind one of the door is a car, and behind the other two doors are ghosts. And obviously, the objective here is that you want to get the car. So, unless you just like goats better than cars, but most of us like cars anyway. So, you start out with no information. You just choose one of the three doors at random. But initially, the host will not open the door. What he will do is he will open one of the other two doors, and say I open door 1, he will open door 3 and say, well, there's a goat behind door 3. The question, and then the host says, do you want to stick with door 1, or do you want to switch to door 2? So the question is, well, should you switch or should you not switch? Pretty much anybody who says this will, well, it makes no difference. You're equally likely to get a car regardless whether you switch or you don't switch, right? Well, let's work out the probabilities and see what happens. So, if you don't switch, then you only get the car if you chose the door correctly the first time. So your probability of getting the car, assuming you do not switch, is just going to be 1 out of 3. But let's say that you do switch, and just for ease of argumentation, let's say that you pick door 1, and then we'll say let D3 denote the event that the host picks door 3 to reveal that has a goat, and then let CI denote the event that the car is behind door I. So with that notation, let's compute these conditional probabilities. First of all, let's compute the probability that the host opens the third door, given that you chose the first door initially. So we can use the decomposition formula. That's going to be the probability that he opens the third door given that the car is behind the first door, plus the probability that he opens the third door given that the car is behind the second door, plus the probability that he opens the third door given the car is behind the third door. And if the car is behind the first door, then if the car is behind the first door, then he can open either door 1 or door 2. It doesn't even matter. There is a 50% probability that he'll open each one. But if the car is behind if the car is behind door 2, then he must open door 3 because he never opens the door that has the car. And if the car is behind door 3, then he cannot open door 3 because, did I say that wrong? Yeah, then he cannot open door 3 because once again he doesn't open the one that has the car. So when you compute out that probability, the probability that he opens the third door is going to be 1 out of 2. So let's say, given that he's opened the third door, what's the probability that the car is behind the second door? Well, we can use the formulas that from the previous slide once again. The probability that the car is behind the second door, given that the host opens the third door, is the probability that the car is behind door 2 and the host opens door 3 divided by the probability the host opens door 3, which then becomes the probability the door that he opens door 3 given that the car is behind door 2 times the probability the car is behind door 2 divided by the probability of door 3, which if you write all that out, that's going to be 1 times 1/3 divided by 1/2, which is 2/3. In other words, if you switch doors, your probability of winning is twice as high than if you kept the original door, so you should switch doors every time you play this game. If you're still having trouble wrapping your brain around that, here's a diagram showing all possible outcomes that you can look at to try to convince yourself that the probability is in fact greater if you switch doors. Or another way that you can think of it is that if you switch doors, you will only lose if you chose the correct door the first time, because if, once again, say you chose 1, if the car is behind 3, he will always open 2. If the car is behind 2, he will always open 3. In other words, if the car is behind either door 2 or 3, you switch if you win. The only way you can lose is if you were right initially. So, even after explaining all of that, I've had people who've taken high-level math classes who are very smart who got very angry with me and said there's no way that can possibly be right, but there you go. Any questions about any of this in today's lecture? Wow, I almost filled the whole time today. Amazing. Okay, this is roughly chapters 1.2 to 1.3 Sellenberger, if anyone's following up on this.